Hello students, welcome to this module on complex analysis, complex numbers and analysis, which is part of the course CHE 641 at IIT Kanpur. Today we are going to discuss a very important result in complex analysis, which is called the Cauchy's integral theorem. Now, before I do that, let me quickly recall what we did in the last lecture, last module, that is. Remember that we tried to first do this kind of an integral. Okay, we took a circle which is centered around the origin, right? Let me draw it slightly better. Okay. Okay, let's say this is a circle centered around the origin, right? And this is the origin. This is an origin. Oops, I'm sorry. Okay. Now the contour is defined as mod z is equal to r. Now this is the radius of the circle r. Now we found this very important result. We derived this integral dz upon z, okay, where the contour is given by, the closed contour is given by this, which is a circle, not just unit circle, it's a circle of radius capital R, let's say. We found this to be 2 pi I. Okay, this is a very, very important result, right? So what is important about this result is the fact that this result depends on the nature of the contour and whether the contour encloses the origin or not. For example, I can take a different contour, okay, I can take a different contour, let's say like this, okay. Let's say this is another contour that let me move it. I want to take a different contour. This is not centered around the origin. Okay, previously the circle of radius was r was centered around the origin. Now let's say that the circle is centered around a point z0. Okay, let's say this is the point z0, and again the radius of the circle is r. Okay, that remains the same as before. The only thing I've done is to move this circle. Remember that this is the complex plane, real part of z, imaginary part of z, real part of z, and imaginary part of z, right? So this is the same as before. Everything remains the same in this contour. This is, let's say, C1, just to distinguish this from this contour. Now I want to know what is dz by z over C1. Now, of course, I have to explicitly do this. So let me show how this is done. So you can think of this as an example also. Evaluate integrals C1 dz by z. Okay, that's a question. Okay. Now to do this, whenever you have a point z0 that is not the origin, now what you do generally is to parameterize this contour. It's easy to think of this circle which is centered around z0 as z minus z0 is equal to capital R e to the I theta. Okay, so z is z0 plus R e to the I theta. Now dz is simply r. R is constant because it's a circle of constant radius, so r cannot be differentiated. Z0 is a constant because z0 is just a point in the complex plane. So the only thing that I will differentiate is this exponential of I theta, which is e to the I theta times I d theta, right? So that is the dz. So what I will then do is integral over C1 dz by z is nothing but theta is equal to 0 to 2 pi. Okay, now theta is not measured around the origin. Remember, the theta is now measured about this circle. So this circle, theta is this because we are now measuring z minus z naught as re to the I theta. So theta is now this. Okay, so let me just move this a little bit. Okay, this is circle of radius r. Okay, now so while theta goes from 0 to 2 pi, it's not circling the origin. Okay, so this is the origin or the coordinate has been shifted to z naught, right? So I'll just write dz, which is r e to the I theta I d theta upon, right? Now z is z naught plus r e to the I theta, so I'll just simply write this. Okay, I can integrate this easily. There is a simple expression for this, and analytically for this integral. This is r e to the I theta plus z naught ln of, okay, theta is equal to 2 pi, theta is equal to 0. Okay, now therefore this integral c1 dz of z is ln, so I have to substitute theta 2 pi and 0. E to the I 2 pi I is 1, so this is ln r plus z naught. Okay, minus the lower limit is still r e to the I 0, that is also 1. So this is 0. So what we have seen is you have this integral, okay, about the origin. When the contour is about a circle of radius r about the origin, you got this very important result. This is a fundamental result in complex analysis. Okay, when in contrast, when the contour or the circle doesn't enclose the origin, we just showed that this is, oops, I'm sorry, this is 0. Okay, this is also an important result, where C1, the only thing C1 has to do is it does not enclose the origin. So there seems to be a fundamental difference between including the origin and not. Okay, so you can also derive the previous result of if z0 is 0, right? If z0 were to be 0, then you can show that you will get the previous result. If z0 is 0, then you have to evaluate ln of re to the I theta between 0 and 2 pi. Okay, this is nothing but, so here I have to use log AB is log A log B. It is ln r plus I theta going from 0 to 2 pi. Okay, so the ln r going from 0 to 2 pi. So this will cancel out. So the only thing I will get is I times 2 pi minus 0 from this term, which is 2 pi I. So clearly the contour, whether it encircles the origin or not, seems very, very important. So this is a very, very important idea about the topic that we are going to discuss, which is Cauchy's integral theorem. Okay, let me take a new sheet. Okay, now I also told you 2 more things or 3 more things. Let me quickly recap that. Suppose I have a contour like this. Suppose I have a contour like this, a semicircle going from plus r to minus r in a counterclockwise sense, right? Again, we showed that dz by z over, let's call this contour C2 as pi I. Okay, now I also showed you that if you had chosen instead from r here to here and then back here, that is, you are going from r, this is real, this is minus r, this is the imaginary axis, this is r real, this is imaginary. So you can go it to from this point to this point like a semicircle, or in terms of 2 line segments like this, right? Here also we showed that dz by z is pi I. On the other hand, if I were to do this, okay, so if I were to, from here I go here, and then from here I come here, right, and then now the positive the counterclockwise semicircle will give you plus pi I. Now this integral is just the opposite of this integral, it will give you a minus pi I. So the integral over this composite contour is 0. Okay, so integral dz by z over this composite contour over, let's call this c2 plus c3 plus c4, let's say c2 plus c3 plus c4 is again 0, right? So what is interesting is that whether this integral of dz by z seems to be 0 if the origin is not included, and it is non-zero otherwise if the origin is included. The reason why I showed these two different contours, you showed we had this contour, and then we had in the previous working we had this contour where the circle is displaced from the origin, okay, where the origin was not enclosed, right, is to show this fact that it is independent of the path. Now what is special about z is equal to 0? What is special about the origin being included or not? Remember that 1 over z is not analytic at the origin, right? So this means that this is giving you a sense that if I integrate a function over a contour where the function is analytic within the contour C, okay, then this suggests that f of z dz should be 0. Okay, indeed this is called the Cauchy's integral theorem. Okay, so let me write this down, the Cauchy's integral theorem. What this says is that if C is a smooth contour that is closed, okay, and if f of z is analytic inside C, then the contour integral of over the closed contour C f of z dz is 0. This is a very, very important result. I cannot overstress the importance of this result in terms of its applications. Okay, so let me box this for you. This is called the Cauchy's integral theorem. Okay, so this is something that we will use very, very frequently. Now how do we prove this? Okay, I have just shown you two examples, and then I have said that, well, it appears like if the origin is not encountered, 1 over z over any closed contour is 0, but then I have to show it in general. Okay, I'm not going to spend a lot of time proving this, but I'm going to just suggest the way the proof goes, and then you can look it up in textbooks as well. But I'll try to physically or try to explain the proof as intuitively as possible. Okay, so let's consider let's consider an arbitrary closed contour C. Okay, now the key thing that we have to know is that this contour can be split into two. Okay, so the first thing is to help avoid drawing such a complicated contour. Let me take a simpler contour. Let's take a circle. Okay, let's assume this is a circle. It's not perfect. So what one can do is you can split this contour into two, closed contour into two. That is, you can say that I'll go counterclockwise, come back like this, then go like this. These are very closely spaced, but I'm just showing it for the sake of visual clarity, and then it again comes back, right? Now it turns out that these two integrals over this path and this path, okay, they are exactly equal and opposite to each other. So remember that the function f of z is analytic inside the closed contour, okay, so there are no singularities. So that ensures that if you integrate this function from this point to this point and immediately if you go back, then these two things will cancel out. This therefore giving rise to this. So I can in principle split this to further, right? I can split this further. I can split one semicircle like this. It comes like this, goes, okay, and then comes back, goes, and then comes back like this, okay. So here again I can show that these two things cancel out, giving rise to this semicircle. So I can keep on chopping these intervals as much as possible, right, as much as I want. So essentially what I'm saying therefore is, if I have an arbitrary contour like this, right, so I can now chop this into several intervals. I'm just showing it for the sake of clarity. You can chop it as fine as you want. In fact, that's what you're going to assume in our sketchy proof. Okay, I'm going to chop it to several, right, and then similarly, so I'll get several rectangular zones except near the edges of the contour, right. Now just as these two things cancelled out, right, these are two adjacent things which I'm drawing like a single line, so all these things will cancel out, okay. They are all, see, I'm trying to draw this like a single line here, so all these innermost parts will cancel out, so eventually giving rise to only the outermost contour, okay. So that is the contour C that we want. So in order to prove Cauchy's theorem, Cauchy's integral theorem, all you have to do is to say that I'm going to take one of these tiny rectangles, right, and then show that the integral that I'm after is 0. So let's take a rectangle, right. Now this rectangle has, this is again real, it's in the complex plane. Let's take one of these rectangles here. Let's take some arbitrary random rectangle from here. That's what is shown here, right. So now these intervals are so small that I'm going to say that this is x plus dx y, this is x plus dx y plus dy, this is x y plus dy, and the contour is in a counterclockwise sense. So what we are interested, so let's call this 1, 2, 3, 4. We want integral f of z dz over this closed contour, okay. Now I can first calculate the 1 and 3 parts and 2 and 4 parts. So let me first do 1 and 3. What is 1 and 3? Here x goes from, you are varying only x, y is kept constant along 1. So this is along 1, x goes from x plus dx, f of x y dx, plus here along 3, x goes from x plus dx to x, f of x y plus dy dx. Okay, sorry about this. Now I can flip this integrand limits in the second integral and say that this is f of x y dx minus x to x plus dx, f of x y plus dy dx. Now I can pull this like this. I can say this is nothing but, I'll put a minus sign, I'll pull out a minus sign as well, x to x plus dx, f of y plus dy minus f of y dx. Now dy and dx are very, very small, so I can write from our basic rules of calculus, I can write this is negative sign x plus dx. This is nothing but partial f partial y times dy dx, right. Now again, this is such a small interval, if I were to use the the fact that within this interval this integrand value will be constant, so I can just simply say this is nothing but minus partial f partial y dy dx. What is this? This is integral 1 plus 3. Okay. Similarly, we can do 2 plus 4. Okay. Similarly, 2 plus 4 will give me, see, only thing you have to realize along 2 is that the integral is I dy. The incremental part is because you are going in the imaginary plane, it's I dy. Otherwise, all these steps are remain the same, and you will get I partial f partial x again multiplied by dx dy. So the entire contour integral f of z dz is nothing but 1 plus 2 plus 3 plus 4, that is equal to minus f partial y plus I partial f partial x dx dy. Okay. Now if I use the fact that f is u plus iv and then expand, this integral becomes minus partial u, so I have to simply substitute minus partial u partial y, okay, minus iv partial y plus I partial u partial x minus partial v partial x. Now you have to watch a bit carefully. If I watch if I look at this term, partial u partial y, right, and then partial v partial x. Okay. Now this partial v from the Cauchy-Riemann conditions, we know that what are the Cauchy-Riemann conditions? If you recall, partial u partial x is partial v partial y, partial u partial y is minus partial v partial x. So these are coming with negative signs, right? So this will cancel out. So these two will cancel out. Similarly, this and this will also cancel from the Cauchy-Riemann conditions. So we have shown that around this small patch, this is nothing but f of z is 0. If this is the case, then this is true for all these small patches, not just one patch. This is true for all these patches. Therefore, if f of z is analytic within any closed contour, then integral of f of z dz must be 0. Okay. So this is called the Cauchy's integral theorem. Okay, this is a very, very important result that we will use very repeatedly. Now I just need to say a couple of more things about this integral. Now one important thing is that this also has a corollary. If f of z is analytic, then integral of f of z dz between any 2 points a and b is path independent. What does it mean? Remember, I have a complex plane, I have 2 points a and b, and I can go between these 2 points in infinitely many ways, right? I can choose many contours or paths. But if f of z is analytic in this domain, in a region in the complex plane, then if I choose the 2 points in the region where f of z is analytic, then one can show that using the Cauchy's integral theorem that the integral is path independent. How do we show this? Let's take 2 points z1 and z2. Okay, let's go from z1 and z2 through a path p, right? And then let's come back from z2 to z1. Let's call this path p12. Let's come back from z2 to z1 using the path p21. But so if the function f of z is analytic, we know that integral of over this closed contour, which is comprised of p12 and p21, f of z dz is 0. This is Cauchy's integral theorem. This is integral over p12 f of z dz plus integral over p21 f of z dz is 0. But p21 is minus p12 prime. That is, I can exactly change the direction. So this can also be written, integral over p21 is nothing but sorry, this is not the path is not negative, the integral. So if I change p2 1 prime as 1 to 2, the same path but with change direction, this will imply that integral p1 to f of z dz minus integral p2 1 prime f of z dz is 0. Okay, so integral f of z dz p1 to, now let's call this for the sake of clarity, let's call this p12 prime because you're going from 1 to 2, right? So let me write this here as well. p21 is from 2 to 1. p12 prime is basically the path, opposite path, but from going from 1 to 2. So integral f of z dz p12 is nothing but integral f of z dz p12 prime. So if the function is analytic, it is path independent. If f of z is analytic, integral f of z dz between any 2 points z1 and z2 is path independent. This is again a very important result. Now one thing that I'll conclude this module with is, suppose I have a contour and let me just draw it properly. Suppose I don't have any singularity within this region, then I can sort of change this contour. I can expand or contract this contour like a rubber band and then say that no, the value of the integral will still be the same. That is, if integral c1 f of z dz is 0, then integral c2 f of z dz is also 0, as long as when you sort of stretch and expand this contour or contract this contour, it should not cross a singularity. Suppose there is a singularity here, and suppose that singularity lies there, and then you are changing the contour, the answer will remain the same. The answer will not remain the same when you change the contour and you encounter a singularity. So that then it's not correct. Otherwise, as long as you do not cross a singularity, you can deform the closed path, and still this Cauchy's theorem holds. Cauchy's integral theorem holds. Okay. What I'll do is I'll stop here. This is a good logical point to stop, and I'll continue in the next module.